Thank you, Peter, for inviting me. I was so excited to be invited to this talk. I was actually planning to originally give it in April from like the back of a car on vacation, but my wife thankfully talked me out of doing that. So here I'm going to give it just sort of a normal talk. So as Peter mentioned, today I work for InfluxData, and I'm also the Apache Arrow PM CET chair. I mostly point that out so that you understand I'm not necessarily without bias as I talk about the technologies in this talk, but I really believe in it. It's not just marketing stuff. It's very cool. Also, as Peter mentioned, I worked for, I think, 6 years at Oracle. I had 6 years at Vertica, and then I worked on Oracle previous to that for a little bit. And I also spent some time doing sort of engineering leadership stuff at a couple of machine learning startups in the interim. So what I want to do today is I want to have a slightly higher, I'm going to talk probably quickly because I have a lot of material to get through, but I wanted to convince you that building a database with some of these open source technologies rather than a tightly integrated system is a good idea. That's basically the plan. So I'm going to review what the technologies are at a high level, how we use them in InfluxDB, right? Not just that this is a good idea in theory. We actually did this with the next version of InfluxDB, which is called IOX, and I will explain how we use them and why. So to begin, I need to spend maybe 5 minutes motivating why we need a new time series database, or perhaps for the people in this room, like what even a time series database is. I'm not sure that they're necessarily as well represented in the database research community as some other types of databases, but basically they're, in my opinion, why do we need one? It's basically the same story that Stonebreaker told however many years ago, where specialized database engines can do 10 times better approximately with specialized workloads. So what is a time series database in particular? Obviously, it's for storing time series, but what makes it interesting from a database perspective? Well, its key properties are it's got the schema on write. So unlike data, it's actually very similar to what Lawrence was just talking about with JSON, right? Where you don't have to upfront explain what the schema is to the system, right? Time series databases are all about you stream data into it. They definitely have structure, but you don't have to, as a user, specify that upfront. So that's very important. And it's not that the schema is totally incompatible. It's that new columns can appear, columns might disappear, but the types and the column names are still the same. You also have this high volume denormalized ingest. Typically, this is like sensors sending data or whatever, and the sensors are very simple. So they send a very simplified data model, which is often strings, right? Like, so it's string data. And not only that, there's tends to be replicated strings a lot, like think host name, right? Or yeah, here you go, host name. They just get repeated over and over and over again. So it's very important in time series systems to get that redundancy out of the input really quickly and get the data queryable, because also, like most time stamps data, the stuff that's most recent is what's really, really important, and the value draws off drastically. So there's a huge number of actually examples of databases that are both open and closed source that have been written about in the literature. The time series databases tend not to be written about as much in the database conferences. I think they're often talked about more in the Unix systems conferences, but they're definitely databases, and there's a list of them. So the classic time series database architecture, right, is basically an LSM merge tree. I don't really know why. Well, that's because it handles the ingest rate nice and quickly. I'm going to skip a bunch of this stuff because I want to get on to the meat of the talk. They tend to be implemented in Golang. They have custom query languages with names like InfluxQL, Flux, PromQL, and LogQL. The reason they have custom languages is because if you've ever worked with time series data in SQL, you have my apologies. Like it's just a mess. And then they also tend to have specialized file formats for storing this kind of data, with names like TSM and TS file and whatever. So what happened several years ago was Paul Dix, the founder of InfluxData, this is prior to me joining, basically listed the types of things you want to put in the next gen database, right? Like it basically wants to have all the fancy stuff that you just heard Lawrence talk about in InfluxDB. So a modern OLAP engine, you want it in a native language, not one with a memory collector like Golang. There's a variety of technical limitations that come with using an LSM tree as your backing storage, specifically about cardinality, which I don't have time to talk about, but it's quite painful. And obviously you want to architect it so you can run it in the cloud and dump a bunch of data using S3 or object store or whatever. And you want to have disaggregated compute where you can split compute and storage if you want, right? So, and it's got to be scalable. And I think another thing that's really important, that's probably at the meat of this talk, is you need it to connect with the ecosystem, right? So Lawrence actually has one example, right? JSON, why is it important? Because people have tons of JSON data. Why do they have tons of JSON data? Well, because it's used by so many tools, it becomes a de facto standard of interchange. Same thing with CSV. And there's other formats like Parquet. So, but the point is being able to interoperate with the ecosystem is really important. And of course, you need SQL as much as time series specific data query languages are valuable. It's also really important to connect with the huge ecosystem that already exists for SQL, and including things like JDBC, which we'll talk about. So, however, it's very expensive to build a new database, as I'm sure people in this room know. I went to Crunchbase and pulled numbers on how much funding various database companies have raised, right? It tends to be in the hundreds of millions of dollars. By the way, InfluxData, it's not on here, but it's basically the same ballpark. So the point is, it's really expensive to build another database, and you basically have to tend to build another company to do it. Really expensive. By the way, same thing at Vertica. Maybe the numbers aren't quite the same, but it's it's definitely the same order of magnitude to build a database system, because it's just like there's a lot of stuff. You got to have smart guys like Lawrence implement cool things like parallelized JSON readers, or whatever, and that's a fairly specialized skill. So the pitch Paul did, and this is basically why I joined InfluxData, was because he already had a database system, and his CEO was like, we can't afford to build another one, right? Like, we're not another company. We already have one, right? So this is my view, the Woody character, the guy who's looking very sad, like, how we have to build another database, Paul? How can we possibly afford to do that? And Paul's vision, he wrote his doc about this, was rather than rebuilding everything again, right, in the classic model where you have a tightly integrated system, you can use open source things like Apache Arrow, Parquet, Flight, and this also talks about DataFusion, which I'll talk about more. But basically, the pitch is, by using those open source components and contributing back to them, of course, you can build a system that has all the properties you want without having to raise hundreds of millions of dollars of VC funding, or perhaps be attached to a world-renowned research institute and have access to wonderful PhD students is another model to build systems. But we didn't have that either. So, yeah, you can read about that if you care. Yeah. So, what do you need, right? If you now break down when you're going to build a model and system, right? Like similar kinds of things. You need some way to store the data. We chose Parquet. I'll explain why in a second. Like, not our own custom format, like literally the Parquet file format. You need some way to represent the data in memory. You want a fast vectorized engine, so that means you need a columnar representation in memory. For that, we use Apache Arrow, which I'll talk about as well. In addition to just having the data in memory, you also need to be able to operate on that, like doing mundane things like multiplying two arrays together. But there's a large number of calculations you need to do in a fast vectorized way. So the Arrow libraries actually provide compute kernels. Right? You need a SQL ability, a SQL engine, which again, I've implemented one before, and it's not easy, not a simple exercise. So the vision is we use this thing called DataFusion, which I'll talk about. You also need a way to transfer this stuff over the network, right, without reinventing yet another network protocol, ideally, which is what Arrow Flight is for, which I'll talk about. And then you also need connectivity to the existing ecosystems, like JDBC, ODBC drivers, and others, and without, again, having to reinvent another wire protocol, which is what Arrow Flight SQL is. So that's the pitch, right? Like, so here's the core. All these are open source technologies, not just open source, but actually open contribution, in the sense that we didn't like write or create any of these. We picked up, we certainly helped along, but the pitch is we can build a system that has competitive performance using open source components like this, and you get it with much more efficiency, right? So that's not just like now we can be richer because we don't have to spend as much money on implementation. It also enables use cases that wouldn't have been possible otherwise, right? Like, so people have access to this technology that wouldn't have had before. And of course, if you use all those technologies, the ecosystem turns out to be great, right? Because you use Parquet files, basically every data system, any OLAP system these days will be able to handle Parquet. It has the schema all stored inside. Arrow Flight, while it's not as widely used as Parquet, it's got a significant list of users. Likewise, the ability to generate data into the Arrow array and memory format, and then share. So you can do, I actually gave a cool talk a couple of weeks ago at a conference. You can actually sort of read data with DuckDB, turn it into Arrow arrays, run it through pandas, right? Then you send it through polars if you want, send it to DataFusion, like whatever, but by using which I'll talk about. So if you're able to pull these technologies off, not only can you perhaps get the implementation benefits, you also are able to reduce, get all this ecosystem benefits. So it's not just a cost saving; it's pretty huge. So with that as the pitch, hopefully you don't all fall asleep now or go to beer or whatever time it is there. we'll just talk about these various technologies, and I'll get through as many as I can before we run out of time. So Parquet, you probably all heard about Parquet. I'll just give a brief introduction and tell you how we use it. So it's a columnar file format. It's been around for 10 years. You know, anyone who's ever worked on Parquet will be happy to tell you like the 5 things that they really don't like about it. But it turns out I think it's basically like the 80% solution or 90% solution. So it works good enough. It's got all the pieces that you need to build a fast analytics system. And it's become super popular. So not only is it widely used, it's got very good compression for a wide variety of data, right? Again, like it suffers from the JPEG 2000 problem where any particular format can probably get 10% better, but the fact that this thing is used so widely on such a wide variety of data, I think means it's here to stay. It of course has a huge ecosystem of tools, like probably everyone. And as I'll talk just briefly, it supports a whole bunch of the query processing tricks you typically would find in an OLAP system that you need to make really fast analytics, and I'll highlight a couple of them. And we wrote a blog post that talks about all of them in excruciating detail, but I'm only going to highlight the big ones. At a high level, Parquet can store 2 kinds of data. It can store tabular data, obviously, right? So this is like an example of the kind of stuff that a time series database has to store, where it's got some strings and it's got some number, right? This is just classic 2-dimensional arrays. It actually turns out Parquet can also store structured data using this Dremel record shredding algorithm. I think the early implementations didn't take a lot of advantage of this, but this is something that I think is becoming more and more important. So that's probably worth its own whole talk. But the point is you can use Parquet to, for example, to store the JSON data that Lawrence was talking about, and its compression is substantial. If anyone's interested, I have like slides from the other talk about that. It's pretty impressive actually. And because once you put in Parquet, you can then do clever things. So what are some of the clever things you can do with Parquet? Let me start by explaining what Parquet file format has, right? So now I'm basically going to pitch you why you don't need your own custom file format to enable fast reads in an OLAP engine. Right? So the way, and I'm going to now describe how Parquet works and then how we can use that to do queries efficiently, right? So Parquet is a columnar format, so that means all the columns, right? Unlike JSON, we have to read the whole thing to figure out where all the columns are. It's stored column by column. It's not actually stored column by column. It's actually stored in things called column chunks. So that's like fixed width, fixed sized column chunks. So that's maybe 100,000 rows or 1 million rows in each, and then those are grouped together in what are called row groups. And so if you're a database execution engine guy or girl, you can imagine immediately what's going to happen here, where because we're dividing the physical storage up, if you can skip or figure out which ones you actually have to read and which ones you don't have to read, it's going to go a lot faster, right? That's like the basic name of the game. Parquet also has a footer that has a whole bunch of metadata in it. So the metadata has information about where to find the various data. I'm not going to talk about this. There's column chunks is actually one level lower than a column chunk called a data page, which is the minimal unit of decoding. But I think maybe for this talk, that's not as super relevant. What is relevant is you've got a metadata footer that has information not only where to find the columns and the row groups or whatever, it also has things like row counts, sizes, min-max values, and whatever. So this, would, I think in the classic database literature be called a zone map. I hope, although perhaps talking to research, I hope I got that right. So but that's, you can then use this metadata in addition to the fact that it's columnar to apply all the classic column store tricks that are described in the literature. So the first thing that almost every reader does, right, because this is the obvious thing to do, is because it's in the column format, if your query only cares about some of the columns, like I stored 3 columns in the table of A, B, or in the file, A, B, and C, and I only need 2 of them for the query, I can just entirely skip everything for column C. Like I don't have to look at the data, I don't have to fetch it from remote store. Right, so this is projection pushdown. Pretty much every Parquet reader supports that. The next thing you can do with Parquet reading is the other classic thing to make performance better, right? In OLAP systems is you do filter pushdown. So you push some of the predicates from the query into the actual filtering and do, reduce work by doing that. So the obvious thing to do, given how I've described Parquet so far, is use the metadata as a zone map and basically skip entire row groups. So because you have the min-max values for column A, right, and maybe it has that minimum is 0 and the maximum is 15 in this example, and this one has 10 and 50. If you have a predicate in your query that says I only care about rows where A is greater than 35, you can skip this entire row group and all the columns in it because no rows can match, right? That's the high level thing. There's actually at least two other additional ways you can do this, because there's finer grained metadata, like zone maps that are attached to each data page. And then you can also do a form of late materialization with this, which again, if you care or are interested in that, you can read all about it in the blog. So I'm not saying this is the only type of filter pushdown Parquet supports, but I'm trying to give you a flavor that, like, here's the file format that everyone uses, and hey, look, you can apply a lot of the classic OLAP predicate pushdown tricks in there. All right, so that's the pitch. So now I told you IOX was all, or InfluxData was all in on Parquet. So how do we actually use Parquet? That's actually the only persistent file format that we use. So I don't have a time to give you the high level architecture of IOX, but at a super high level, it's got a write path and a read path, which for anyone who studied distributed database, this will not be shocking, right? So basically the write path gets data that comes in this is called line protocol. It's like a CSV-like file format. It's basically all text. It's not quite CSV, but it's close. It has slightly more structure. Then there's a tier of machines that are responsible for parsing that using tricks like Lawrence was describing. And eventually they'll periodically write the data to Parquet files and write it to object store. Right, so this is like S3. And then when a user's query comes in, there's another system called the query that actually has the query planner, runs it. We'll fetch data from the object store, probably with a whole bunch of sophisticated caching here to avoid the latency, in an ideal case, plus talks to the ingesters to get the data that's not yet persisted, right? Because it's got this leading edge, which is the most important stuff typically, and returns the values back. So like basically any data that's stored in IOX is stored using Parquet. And then these queries use all that predicate pushdown stuff that I was referring to make the queries go really fast. And we definitely contributed a bunch back to the, maybe I'll talk about that later. All right, so is that, I think hopefully that's not too much, and we'll just keep blasting ahead. So there's our pitch, right? You don't need a specialized file format, you can do it with Parquet. So let's talk about Arrow, because I told you Arrow was another major component. So what is Arrow? Arrow is like a memory format, a standard memory format. To be honest, if you're going to generate an array of 64-bit floating point integers, there's really not that many ways to represent that in computers. So it's not that like Arrow is innovating in like the basics, stuff like that. The innovation of Arrow is that it standardizes it. So for example, when you want to represent nulls, do you represent it using a null mask where the one is a null, or is it with one, or is a validity mask where the one means it's valid? Not, both of those are fine choices, but like you got to have everyone agree on which one it is. So Arrow does that. It also has support for structured types, and they do the nasty stuff like Lawrence was hinting at, of like dealing with timestamps and the interval type and how the time zones are represented and how you represent structures. And like, I don't think any of that's particularly novel, but what is important is that it's standardized and that you don't have to reinvent it in your new engine. At least that's what the value is for IOX, right? So we don't have to reinvent how to represent timestamps and do timestamp arithmetic. It's just someone's already just standardized one. So I'm going to talk about record batches more in the rest of the talk. That's why I have to introduce the terminology, but a record batch is just two columns, two of these arrays with a name. The arrays are types, so they have types attached to them, but the record batch also has column names. That's it. So, but when I talk about record batches, it just means some number of arrays together. All right. Hopefully that makes sense. I know I'm going fast, but I have lots to tell you. So the Arrow itself has native implementations in 7 languages, and then it's got bindings in 5 others that basically are on top of the C++. So it's got native implementations in all these different languages, right? Obviously, Rust is one that was important for Paul, so we implemented Rust. It's got a native implementation there, and includes both the implementation of the arrays, but also the kernels, right? So compute kernels, I keep mentioning that term. I don't know how many people are familiar with that. I thought maybe I'd give you a taste of this. Again, this is not like the most earth-shattering of kernels, right? So like if you have 2 arrays and you're trying to compute the elements where one is greater than the other, right? Where the green array, where the green array is bigger than the blue array, I'm sure probably everyone in this room could figure out how to write code that would do that, especially if these are primitive types. And probably that code would get vectorized fine by the compiler, but vectorized in the sense that you can use SIMD instructions and do them a couple of chunks at a time and handle the final case or whatever. this is the kind of stuff, if you've ever implemented a vectorized execution engine, you need to make sure your kernels are doing this, right? You compute greater than on 2 columns, you've got to make sure it's like doing it as fast as the hardware can do it. And so these kernels are, the point is the kernels are built into the Arrow library. And of course we help and make sure them, so you can invest the time and effort making sure they're operating very quickly, again, without having to implement them specifically for IOX, right? There's nothing specific about computing greater than for a time series database. So if we could reuse someone else's implementation, which is basically going to be the same as anything you come up with, everyone wins, right? So that's the goal. Yeah, and I have greater than, right? That's a simple one. There's like 50 different ones, and they do things like handle null masks and deal with different data sizes and all sorts of stuff. Which again, none of that's like, I think, super interesting from a database research perspective, but like when you actually have to implement the system, it's a lot of work to get it like working with all the different types and whatnot, making sure it works nicely with scalar values and non-scalar values. All right, so how does IOX use Arrow? Well, it uses it a lot indirectly from DataFusion, which I'll talk about in a moment, but it also uses it directly. So I told you, this ingest path takes a CSV-like type of data format, which is called line protocol, and it converts it internally into some memory buffer that conforms to the Arrow format. And so as the data streams in, it gets written to this buffer, right, parsed and written to the buffer, and then over time gets snapshotted to record batches, right, which if you've implemented a streaming system, you don't want to have like one giant record or one giant chunk of data for each for your input. You need to break it up into pieces so you can stream it through. So that's exactly what happens in this case. They get snapshotted to things called these record batches, and then we can feed those record batches through the Parquet reader, which is, or writer rather, which is written in Rust, right? It's the same part of the same library, part of the same Arrow implementation. Well, no, that's not true. The Arrow implementation of Parquet, or the Rust implementation of Parquet, can write Arrow record batches directly, right? So you basically just feed it a bunch of record batches, and it knows how to write it quickly and efficiently into Arrow. And maybe that doesn't sound amazing, but it's non-trivial. And the fact that like Parquet has its own type system, right, that's different than Arrow or different than whatever system probably you implemented yourself, right? You have to do this mapping from the Arrow type system to the Parquet type system. And by the way, that's really messy when it has structured types and lists and nests, and when there's nullable, and like it's a mess. Yeah, I see Lawrence shake his head. Yeah, he's dealt with stuff like that. And then but yeah, so frankly, we helped implement that in the Rust Parquet writer, but we weren't the only ones who did it, right? We had help from other people who were using the same code, and I think with a small number of us, we were able to get that kind of functionality right, so that the Parquet writer in Rust now handles arbitrary structured nested types. If you want, we wrote a blog post, you can read all about that, which is kind of wonky, but I think it's important. Also, I'll hint a little bit in the future, not only do we use record batches in an intermediate format to send to the Parquet writer, we also use them when the querier wants to get access to the most recent data, right, that's not yet persisted into Parquet. It actually gets the data back in record batch format over something called Flight, which I'll talk about. Which again, it sounds obvious, right? But if you're not careful, you end up having to like take the data however it's represented in memory, serialize it to network somehow, send it over the network, do the opposite on the other end, and there you go. So by using Arrow, you have all that stuff built for you. All right, I'm going to skip a lot of this because I think it's not as relevant. The point of the next couple of slides, which I'm going to rip through super quickly, is that Arrow actually didn't come out of the database world. It actually came out of the data science world. And basically the observation in the data science world from one of the founders of Pandas, which is a very common Python-based data processing library. He basically observed that you can apply a whole bunch of systems techniques to data science, right? So here's some slide from his like back 5 years ago. Not that what's on this slide is important. I think what he did that was really valuable was, rather than just go apply this stuff directly to Pandas, right? He instead applied it to Arrow, right? Built another layer in there that then Pandas is in the process of adopting, but also has then spawned its use elsewhere. So it didn't just help Pandas, help the whole ecosystem. And I think that was a very valuable choice. So the original pitch is, right, you can, instead of having to copy and convert all these from one system to another, you can just use Arrow memory. This actually does work. I forced myself to figure out enough Python to be able to talk about how to use several different tools, and it's very cool to see how this works. So if anyone's interested, I'd be happy to show them that. I mean, oh yeah, this slide's from like 5 years ago. I made a new version that maybe has some more modern technologies, but it's the same story, right? Where if you're just passing data back and forth in memory, doing it with Arrow is very compelling, because then each of these systems doesn't have an end-to-end problem. It has you just convert to Arrow, and there you go. All right, so let's talk about DataFusion. If I may switch topics. So we have Arrow is the in-memory format. Right now, if you're building a database, you almost certainly need something that does SQL. What is DataFusion? Well, DataFusion is the thing that does SQL, among other things. It's a query engine written in Rust. It uses Arrow as its in-memory format. I'll talk about that briefly in a moment. It does things like SQL, and it has a data frame API, and it has optimizers and all the good stuff. You can use these together or independently if you want. It has built-in support for CSV, Parquet, JSON, Arrow. And we've seen people use it directly as an embedded SQL engine. They use it like we used it at InfluxData as a foundation for building a new database. And there's also people who use just pieces of it for building either like special query engines or accelerators for their existing query language, or as a research platform, or they just want to write a CLI that like transcodes data from one format to another, and they don't want to have to worry about how to like implement fast sorts and stuff. And people used it to swap out Spark runtimes, much like Photon, but for their own uses and that sort of thing. All right, so what is, like, at a software level, what is it? It takes, I always like to think about stuff as an input-output diagram, right? So what is DataFusion? The component, it takes a SQL query in, or a data frame, has a data frame API. You have to feed information about what catalog exists, so basically what tables, what their types are, that kind of stuff. And then eventually, when you run a query, you have to feed it the data that corresponds to the stuff that you told it about in the catalog as record batches, right? As these Arrow record batches, and it does its thing and produces record batches out the other end. So that's like, you have Arrow in one side, or it can be Parquet or some of the file formats it supports, and you get record batches out the other. And now I've already told you, with these record batches, you do all sorts of clever things, like you can pass them on to some other system you care about. You can write them to Parquet, you can write them to CSV, you can write them to whatever. So it's very, I think, compelling from that perspective. So if you look internally inside the DataFusion system, if you've ever seen the inside of a query engine, it will not at all be surprising, and that's by design, right? This is basically like the classic textbook query optimizer. So the way it works is you have things that provide the data, like Parquet files or CSV or whatever. You can provide, then there's a front end that translates SQL, like it parses SQL and turns it into plans. There's like that data frame library does the same thing. It generates there's a logical plan representation, right? So that's a relational operator tree that if you've ever looked at the inside of a database engine, they all have some version of that. There's a variety of optimizations and transformations that happen on that logical the logical plan. There's a lower level description of those relational operators that has more details about physical properties like sort or sortedness and particular algorithms and whatnot. And then there's actual optimized implementations that do the sorting or the grouping or the hashing or whatever. Now, I just told you that's not particularly novel. I think what's quite clever about DataFusion and what makes it so powerful is you can extend it basically anywhere. So you can extend it as different data sources, which we do in IOX, right, which is the influx data. Then you can make different front ends, right? Because all you got to do is write code that generates one of these logical plans, and then you can use the rest of it, which we do that also in IOX, which I'll explain. You can extend the relational operators in whatever ways you need, right? If you want to write queries that have semantics that don't fit into the defined relational operators that come with DataFusion, it's okay. You can just extend it yourself. We have a couple of those that I'm not going to talk about, but we definitely do that in IOX. You can write your own transforms. Likewise, you can extend it at the lower level execution plans and the operators. So the point is you can basically hook in whatever you need. So you can use this as a way to start because it has all of what you need for basic SQL, and then you can add whatever you need on top. And that's what we do with IOX. There's several other projects that do something similar. Yeah, so let's see. Yeah, so here's how does IOX use it? The way IOX uses DataFusion is basically anytime you touch data, it goes through DataFusion plan. it took me non-trivial amount of time to convince people early on. They weren't necessarily sure about that. In particular, once data gets turned into record batches, how do you generate Parquet files? And how do you generate, and then obviously the queries go through DataFusion, but the physical reorganization does as well. One of the reasons for that is, in my mind, maybe it's just because I'm a query engine guy, they're all just moving data around. It's all the same stuff. But more practically speaking, it's so that you don't have to reinvent execution machinery, like the fact that it can stream and then it's got to fast sort and merge. And then when you optimize those things and you spend time making them faster, they can now be applied to your physical reorganizations, not just to your query plans. And there's you got to worry about worker pools and resource limitations and all that sort of stuff. All the same challenges that you run into in query execution, you tend to run into in data reorganization. So that's it. And the other thing, of course, is that the more we could push into DataFusion. By the way, we didn't make DataFusion at first. It was a project from someone else that we subsequently helped along by investing in, but we didn't do it. And of course, by pushing more of it upstream, you have more of a chance of other people helping you both to contribute optimizations, right? Like, for example, the implementation of out of memory sort did not come from us. It came from some other guy who was doing, I can speculate as to the reasons why he did it, but he did a good job. And we didn't do it now, but now IOX can do it. And so it's pretty neat to see how that works. So here's the high level system diagram of how query processing works in IOX. IOX can support several different types of queries. There's an internal API. It's called the storage gRPC API. That's how it implements something called Flux and some other stuff. So this is basically an internal InfluxData thing that has very specific InfluxData semantics. There's of course SQL, which we can just use pretty much unchanged, the SQL front end from DataFusion. There's also a specialized language called InfluxQL, which is one of these specialized time series domain specific query languages that we also we basically have a front end for that turns it into logical plans. And then there's this thing which makes the specific plans that we need for running reorganizations, which is compactions or splits basically. So what's neat about it is they all turn into this logical plan format that's part of DataFusion. And then from that point on, all of the rest of the infrastructure is the same. So like it goes through all the same optimizations, including all the classic pushdowns and filtering and all the stuff you'd expect to find in a query optimizer. It does all the physical planning and the sort optimization, and then it uses the optimized execution, implementations, the actual operator implementations, and then it spits record batches out the bottom, as I mentioned. It streams of record batches again, which is important for a streaming engine. And then depending on where the query came in, it goes to different places. For the specialized internal API, there's some specialized code that we have to maintain to turn it into the format that's required for that. If it goes to Parquet, we just send it to the Parquet writer, which is very convenient. Again, we work on this, but other people do too. Or if you're sending it to a client, you could send it over Arrow Flight, which I'll talk about in a second. Okay, so let's see, do I have time to talk about this? Yeah, I can briefly mention this. So I thought it might be interesting to this audience, maybe why DataFusion uses Arrow internally, right? But you don't need to, right? So DataFusion uses Arrow internally in the sense that like all the internal implementation stuff uses Arrow. You don't, which is not required. I'll explain the other option in a second. It's something that other systems have been doing as well. Polars does it, and Acero does it. The pros is, of course, you get fast interchange, which means if you want to share Arrow data with other people, that's great. You don't have to do any translation. I think, frankly, the bigger value of using Arrow internally is that you can reuse those Arrow libraries, like I was talking about earlier, and so you can amplify your investment in open source and be able to get benefits back from the community. I don't actually think Arrow is as optimal as certain other options that you could, right? So in particular, there's certain things we might want to do in the query engine that you can't represent as Arrow arrays. And like, for example, do the small string / German style string optimization, or do certain kinds of list encodings or whatever. So like, that's the other option, which I think is what, as I understand, what Velox and DuckDB do, which is they use their own internal formats for arrays, which, you can probably imagine, are probably pretty similar to Arrow arrays because there's like not that many ways to represent an array of floats. But then they have to do a conversion step on the output. And again, I don't think the conversion step in my mind is the huge bottleneck, right? Like maybe it's huge, but it's not that big of a CPU deal. What's really important is that now you've got to maintain all of not only all the complicated operator code, but also all the lower level kernels and the representations and the mappings and all that stuff, which you can do. It's just requires a bigger investment. Yeah, and I think you can get faster speed. So the pitch, and the theory is you can get, I think this is what I just said, but the theory is you can basically get similar performance out of using Arrow even than a specialized structure without the same level of investment. And I think, picking benchmarks, however one likes to pick benchmarks, I'm pretty pleased that DataFusion, here it is typically within a factor of 2 of DuckDB. Now maybe people think that's terrible, but I think that's actually pretty good given all the other things DataFusion does. And of course, we're making it better. And if you pick if you pick very specific benchmarks that are really important to us, like very specific Parquet query times, you can actually make it go faster than DuckDB. But I'm not going to claim this is like a super important use case. But I think it does basically broadly show that you can get a similar level of performance by using the generic kernels at a much less level of investment. Yeah. Okay. So probably should stop for questions, but I'm not going to, so I can get through the rest of this. Arrow flight. So I've been talking up the benefits of Arrow and the in-memory representation. Now, if you're building a database in the day and basically in the last 30 years, you're going to need to somehow transfer data over the network, either because you're running on a client-server application and you need to send data to the remote servers or the clients that are running remotely, or you've got a distributed database, you got to send data between the nodes. You're going to have to do it. Why do we need Flight? What is Flight odd? I would like to bring your attention to a paper written by some people at your university, right? This paper is the case for why you need something like Arrow Flight. And the core, which is, it's called the Don't Hold My Data Hostage, a case for client protocol redesign. Also the founders of DuckDB, for those of you who don't recognize those names immediately, and their CWI, I don't know, alums are definitely still associated somehow. And if you look at basically this paper's pitch, it basically says the client protocol are the bottleneck. If you just want to read large volumes of data from some of these analytic systems, it can take like tens or hundreds of times longer to read the data out than it did to run the query, which they attribute to the crappiness of the client protocol. Oh, I shouldn't say, no, that's too pejorative. They attribute to the fact that client protocols were designed for transaction processing systems, which is true. Yeah, and then, so this Flight is one of these versions where it's gonna basically keep the same column of representation and find a fast way to send it over memory, right? So I always like to think of Flight, well, what is Flight? Well, you've got this Arrow memory model. If you're passing data around between processes or within a process, if you want to pass it over the network, you just got to wrap it a little bit with some network stuff, and it's sprinkle some network stuff on there. You got Arrow Flight. The networks, yeah. So what Flight is the gRPC-based protocol that you can send Arrow arrays over the network. If you designed a protocol for doing network communication, you would probably come up with something very similar to Flight. It has its own peculiarities, but it's basically got everything you want, which is, it's got some notion of that there can be a metadata server, and you run that and you get back some information about where to find the actual results, and then you can send a request to the different servers. So, it can handle this where one client can talk to multiple remote servers, one client can talk to one, and when it streams the data back, it sees streams of Arrow arrays in a format that you don't have to copy, zero copy. I like to call it zero copy. I get in trouble from some of my more pedantic coworkers because they tell me it's not actually zero copy because there's some copies in the network stack and maybe in the gRPC implementation of Rust, but it's like you certainly don't have to do anything. I'll just do a mem copy and it's plenty fast. So how does IOX use Flight? And again, like if you have your own system, I saw versions of this in Vertica, right? And I'm sure every other database system has versions of this. It's not that sending data in a columnar fashion over the wire is particularly novel. What's novel is that I don't have to go implement that again, right, and handle all the error cases and the encodings and the blah blah blah. Like it's in a library that you can already use, and it's fast. So when our users query via Flight, the IOX native query protocol is actually just a small layer on top of Flight. So it's just implementing this. So our clients is literally like a Flight client with like a small amount of client specific data on it. Also, not just is it on our client protocol, it's also the internal protocol that gets used when the query talks. Oh, sorry, yeah, I'm getting ahead of myself. Yeah, so remember the query comes in, the ingester does things. So the responses comes back on flight as record batches. But also, right, this line I've been trying to show where like the query asks the ingester, which is for the data that has not yet been persisted, right, the most recent data that's not yet in Parquet files, that protocol also happens over flight. And again, like, it's not that flight is like the most optimal thing you could possibly design if you're doing it, but it's like 95% of what you'd probably do, and we didn't have to do it, and we don't have to maintain it. Well, it's not like we don't have to maintain it. What we do is we along with the rest of the community maintain it. So our investments in the maintenance are amplified significantly. So it's very cool. Like, it's literally the same code that transfers data between here and here, which, for example, at Vertica, it was different protocols. All right. So yeah, that's what we do. This is, I went through it quite quickly, so you probably maybe didn't see it, but if you looked carefully at that other protocol diagram, you might assume that you have to do a 2-network round trip to actually make a query run. That's not, you can basically bend the flight spec a little bit and teach it how to skip the first round trip. So you can still do single request, get the stream of responses back. You don't have to do a double round trip to run queries on IOX. And we do it by abusing flight a little bit, but it's not a bad abuse, I don't think. It's basically teaching the client about some stuff the server is supposed to know. All right, so Flight SQL, I'm almost done. Flight SQL is like the final level on top of this thing. Right, so I know I'm going quickly through this. For that, I apologize. I also wanted to point out the mere fact that like I'm talking about that I have to like the breadth of technology you need and the capabilities you need to build a database system, like it's big, it's very big. And so that's why I think being able to use existing implementations, right, and other open source technologies, like that's what's going to allow people to build many new database systems and effectively commoditize these fast OLAP engines. It's because you're not going to have to go reinvent all this stuff that I'm explaining, right? Which I'm sure, the smart people in the room in CWI can absolutely do it because they've had a history of doing that, right? But it does take time. All right. Sorry. With that interlude, Flight SQL is one level on top of Flight, right? So Flight doesn't have anything to do with SQL. It's just a matter of transmitting record batches over the network quickly in a streaming fashion. And then people observe basically, a very important stream of data you might want is SQL. And I'm not going to read all this stuff. You can read it. This is the blog for Flight SQL. I'm going to instead show you some pictorial examples of why this is valuable and maybe tell you a parable or two of stuff from Vertica. So the way client-server databases tend to work is that each server has its own database-specific protocol that it implements. Postgres, it's called the front-end, back-end protocol, I think because they don't have any other name for it and they just needed something. So it's called FTB, or perhaps that's what the source file name is called. And each client that wants to interact with the database doesn't know how to talk this database-specific protocol. It knows typically how to talk using a standard interface, like JDBC is like an old one, but it's like one of the first really widely used interfaces. And then the implementer of the server provides an implementation of that interface that talks the specific protocol, right? So that means now you can have multiple client applications that don't have to know anything about, in theory, about the server that's behind them. And this is good. So this is how database client connectivity works today, basically. I should point out it's not just JDBC and ODBC, right? That's probably dating myself to like back when Vertica was really popular. These are still important standards, don't get me wrong. But what also has happened is that now typically the pictures tend to be worse because not only do you have to do these JDBC driver, the JDBC and ODBC driver, you tend to have to implement a specialized implementation for each one of the major programming languages, which has its own sort of native database interface API. Like, for example, I don't know how to pronounce that, right? But this is the one for Python for Postgres. So it's like another implementation of the Postgres wire protocol in Python. So this is what people were talking about early on doing at IOX, which was terrifying, which was basically, because we don't want to have all the problems that the nice, kind folk at CWI explained about having bad protocol, so we're going to use this nice high performance record batch stuff, send it over the wire, but then we'll write our own JDBC driver, right? And that will be able to take this flight protocol I just described, turn it into this interface and go. So that seems like the obvious thing to do if you've never done it before. It turns out, having seen that done first-ish hand at Vertica, and if you look at it, like there's a whole company whose whole basically reason for being is to help people implement JDBC drivers. So that should give you some sense of like that it's not trivial to do this. It's very not trivial, and it has to do with like because you have to map your types to the thing types, and there's a huge metadata surface and blah 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 blah. Like rather than getting into it, just like I saw this took a whole team to do, and we didn't have a whole team to do client drivers, so I lobbied hard not to do that. One thing they did try, which is also a very popular strategy, by the way, is to take because JDBC drivers, or by extension the other drivers, are so complicated to implement. Another classic strategy is, well, we're just going to reuse someone else's JDBC driver. Like Postgres tends to be a popular choice. But to do that, you then need to translate whatever your database's native protocol is into the Postgres front and backend protocol. So actually, we had an early version of this. It was called PIGOX. It was awesome. In some version of awesome, it translated these record batches into the front end backend protocol, and then we could use the JDBC driver, and it kind of worked. First, when the CWI paper says that it's not good, not very efficient to send the data over, and then you actually look at what's going over here, it's like strings. Like yes, there is a binary version that's slightly better, but like it's terrible. Like so performance-wise, this is really bad. The other thing that people don't fully appreciate when they start doing this is that any actual client will interrogate the JDBC interface for a bunch of metadata, like what the table names are, what their types are, that kind of stuff. And then this JDBC driver does a whole bunch of queries back against special Postgres-specific metadata tables. So even though you can talk the protocol, like actually making this client work is quite a bit harder because you need to implement the Postgres metadata API, which again, if you haven't done it before or you're just doing a demo, doesn't necessarily occur to you. So the really cool thing, here's what we actually ended up doing. We didn't want to change this. What we really want to do is we want to use someone else's JDBC driver. So there's a Arrow Flight JDBC driver. So if you implement Arrow Flight, you can use that driver. And then we have to implement Arrow Flight. And Arrow Flight is some version on top, some layering on top of Arrow Flight. Flight SQL. So Arrow Flight is what I just described, right? That's like how you can just send record badges over the network. Arrow Flight SQL is a layer on top of that uses the same mechanisms to send record batches, but has additional metadata APIs, right? Like first-class metadata APIs that you have to implement that says like what the tables are, what their types are, and provides a bunch of other metadata. But if you implement that API, Flight SQL that is, then you can use this JDBC driver and it works. And so this is what we've done. We contributed both to the JDBC driver, worked a bunch on the Arrow Flight SQL implementation in Rust, and it's working shockingly well. So I'm pretty happy with how that worked. Yes, and you can like do clever things like connect Tableau to a time series database without a bunch of translation logic in between, which is pretty neat. All right, I think I want to stop there. I have some other slides about like why open source is awesome and why open source isn't always like there's open source versus open contribution, right? Like people can develop in the open versus like how do you actually encourage a community to help contribute, right? Because that's the whole point of that was basically the premise of using these technologies, so that we wouldn't be maintaining the whole thing. And so, I mean, I'm a huge fan of the Apache Software Foundation. It has a whole process to support this piece of support that, but I want to stop maybe early to leave some small time for questions. And I know it's like beer o'clock probably in Amsterdam. So yeah, with that, I'll just skip this stuff, and say it's been good. Is there any questions?